Hello and welcome back to Calculus1 Saturday edition. We're going to talk about 3.5 derivatives of trigonometric functions. So for this, we don't need a theory of trigonometric functions in order how to set them up in triangles and so on. What we need is some knowledge on identities so we can simplify in some cases. Now, we are going to memorize those shortcut formulas, 6 trigonometric functions, 6 formulas. But before we do that, we are going to take a look at one of those, at sine. We can do cosine as well, whatever. How it's done using the limit definition for the derivative, the one with the limit when h goes to 0, the difference quotient. So we're going to develop just one of them and then talk about how to get the other ones. Your job is to memorize those 6 because, again, I say memorize because these are shortcut methods. So we're going to see what it is to take the derivative without. So our goal is to find the derivative of sine x. And what is the derivative of sine x? Well, we are going to do the limit as h goes to 0 of sine x plus h minus sine x divided by h. So that's the setup. This is the way we know to take the limit from 3.1. Sorry, to take the derivative using limit from 3.1. And now let's see what that entails. Now remember, you're supposed to copy the limit in every step all the way down to the end. So you take this, and now we need that formula from pre-calculus, which is the sine of addition of two angles, which would be sine x cosine h plus cosine x sine h, and then we have minus sine x divided by h. Now this term and this term both have sine x, so we can factor. And that's going to give us limit h goes to 0. And when I factor that sine x, what's left is cosine h minus 1. And I still have the second term of cosine x sine h. There, everything divided by h. The limit laws tell us that we can, since these are two separate fractions, right? We can separate this into two separate fractions and give limit to each one. There was a limit law that says that, right, if you have addition of two functions, you can give limit to each one independently. So we have the limit, h goes to 0. We have a sine x cosine h minus 1 over h plus the limit h goes to 0 of cosine x sine h over h. Now, one thing we talked about before was whatever the variable is in the limit is the variable for the problem, and other variables are all constants. So these are the variables, that's a constant in eyes of the limit, because the limit is operating on h, not on x. So we can kick out sine x and just have the limit h goes to 0 of cosine h minus 1 over h, plus kick cosine out and have the limit h goes to 0 of sine h over h. Perfect. Now, this limit here is 0, and this limit here is 1. Now, these limits are listed as special limits to memorize in the calculus textbook. Now, I do not bother students with memorizing these limits because in chapter 4, you will learn the proper way to solve these limits, which is the reason why I do not expect you to memorize these limits now, because eventually you are going to learn how to compute them. So it's better to know just one way than to memorize 100 different things. So now, if you want to, I think these limits are given in a book. Let me real quick find it. On page 171, you will find these limits listed. So this gives me sine x times 0 plus cosine x times 1, which is cosine x. And at this point, you guys learned that the derivative of sine x is cosine x. This is the formula. And you, instead of working out this limit, every time to find the derivative, it's easier, I guess, I hope, to memorize that derivative of sine is cosine. So you can go and do exactly the same procedure for cosine x and do these calculations. Cosine formula for that addition is cosine x cosine y minus sine x sine h, actually. So cosine x cosine h minus sine x sine h. If you want to do this same procedure to practice it, to learn it, if you want to use it for cosine. Once you do that, you will discover that the derivative of cosine x is negative sine x. And this is another formula which we are memorizing, so we do not have to do this to find the derivative. Guys, these procedures are there for ln and e to the x, and for every single function you can think of. There's procedures with h and x with the difference quotient, right? They're there for every single one. We are learning these shortcuts so we don't have to do the limit. That's what the chapter 3 is about. Let's learn all of these shortcuts and memorize all of these shortcuts so we do not have to do the limit when we need the derivative. We can just say, oh, we can use the power rule, or derivative of constant is 0. Derivative of e to the x is e to the x. Right? There is a way to show all of those things as you go along. The next one is the derivative of tangent. What do you think? How could we possibly show the derivative of tangent? Anyone? What can we do?
Convert it to the quotient identity.
Excellent. Use the identity to turn it into quotient. What is the identity?
Sine over cosine.
Beautiful. Yep. Excellent. Sine x over cosine x. Perfect. And now use quotient rule. And all four are done this way, right? What is secant? Secant is
1 over cosine.
1 over cosine. Perfect. So all other four will be done by converting them and using the quotient rule formula. So now for our quotient rule, what do we have? We square the cosine, then we copy the cosine, take derivative of the sine, we know that's a cosine, minus, copy sine, and then take the derivative of cosine, which is negative sine. There we go. Perfect. So what do we have? We have cosine squared x plus sine squared x divided by cosine squared x. And what's this on top?
It's 1.
It's 1. Sine squared plus cosine squared is equal to 1. That is what we call a Pythagorean identity in pre-calc 1. Very good. So we have 1 over cosine squared x. Now I will remind you that that can be written this way. That's algebra. And what was 1 over cosine?
Secant.
Excellent. So we just learned that the derivative of tangent x is secant squared x. You are memorizing this in the red box, so you do not have to do this stuff every time when you have a derivative of a tangent, which is going to be a lot, especially in Calc 2, when you get into trigonometric integrals, trigonometric substitution, the entire chapter 12. There's going to be a lot of derivatives of tangents and trig functions, obviously. So learning this is very, very important. Memorizing all of these 6 rules. Well, 4, not all 6, but whatever. I'm just going to write the other ones because now you know, if you care, if you're a math major, if you are electrical engineering major, mathematics is either 100 or 97% of your life. So ability to work out these calculations quickly and efficiently, right? You should practice. But for everyone else, just memorize the formulas. We have the derivative of secant x, which would be secant x tangent x, and finally the derivative of cosecant x, which would be negative cosecant x cotangent x. And I'm just going to put those in another box. Now, unfortunately, I have to write all of this again so that we can take a look at the ways of how to memorize this and so on. So here we go. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. And the derivative of tangent x is secant squared x, and the derivative of cotangent x is negative cosecant squared x. Finally, the derivative of secant x is secant x tangent x, and the derivative of cosecant x is negative cosecant x cotangent x. Can you tell me what you see in the cloud over here? Apart from saying the obvious, I see the derivatives of trig functions. I want patterns. I want interesting stuff. So stare at this and try to make some conclusions. And just say it when you see something, or you think you see something.
Tangent and the inverse tangent are both squared.
We did not have inverse tangent, careful. The derivative of inverse tangent we're going to learn later. You meant cotangent, and yeah. That's perfect. That's exact. The derivative of tangent inverse, that's going to be, I believe, in 3.10, is going to be 1 over 1 plus x squared. So that's going to be completely different thing. Cotangent is another function. So you said they're both squared. Perfect. So we see the form, right, that if you have a tangent, which is sine over cosine, and cotangent, which is cosine over sine, is going to be square and a square. Excellent. That's one of them. What else? Just say it.
The derivative of both secant and cosecant, secant, yeah, cosecant and cosecant. Correction, secant and cosecant, they both have their, I guess, same function, or
same form with appropriate functions, right? Mm-hmm. Excellent. Yes, that's all perfect. In some sense, right, this side behaves the same as that side completely, right? Or we see something really interesting. Do we see anything interesting between two sides?
I guess the left side is all positive and the right side is negative.
That's exactly it, right? All of the cosine, cotangent, cosecant, so all of the cos are all negative, right? And we see the same form: sine, cosine, cosine, sine, tangent, secant squared, cotangent, cosecant squared. It was a cotangent, therefore negative. Secant, same form as a cosecant, but the cosecant, right, with the co, is negative again. Can you tell me what are the trig derivative pairs? And try to guess what that means. Trig function derivative pairs.
Is it the last row? Derivative of secant x and cosecant x?
No, that's not it. Okay, that you see two things. It's getting there though.
Is it the left side and the right side,
nope.
like going across?
Good guess, but no. Trig function pairs through the derivative. This one is a little bit tougher to see, but it's going to be the most important of everything we had so far. Especially for your Calc 2 later on. Function pairs. Pair up two functions. Just give me any two trig functions as a pair.
Sine x and secant.
Good. Can you find any formula that pairs sine and secant? On the screen? Can you pair, do you see that pair anywhere? Sine with secant. That's not a trick question. Use your eyes, look at the 6 formulas. Do you see a sine secant pair anywhere?
No.
No, perfect. Give me a pair. So I asked for any, and that was a fair, right? That was fair. I asked for any, you gave me sine secant, and I said, do you see any of these formulas that have sine and secant as a pair? You said no. Perfect. Now look at the 6 formulas and give me a pair of functions that does appear in a formula.
Sine and cosine.
Beautiful. Give me another one.
Tangent and secant.
Good. Give me another one. Anything else?
Cosine and cotangent.
Beautiful. No cosine, cosecant and cotangent.
Oh, right, yeah.
Yep. Okay. So, perfect. Do you see that you do not have any other pairing in derivatives? Sine is always with cosine in the first row. Secant and tangent are mushed together. Cosecant, cotangent mushed together, and they do not crisscross. So we are not going to find sine cotangent pair, sine cosecant pair. There is a formula that connects sine to cosecant, right? 1 over sine is cosecant. But in the derivative pairing, in the calculus pairing, it is always sine with cosine, and always tangent with secant, and always cosecant with the cotangent. And they do not cross anywhere. So there is a lot of symmetry here. There is a lot of kind of pattern. And if you stare long enough at those patterns, you will pick them up. In addition to memorizing these 6 formulas, do you have to memorize 6 formulas? Or is it enough to know this? Do we all see that if you just know the left side, the right side is immediately given, or a common sense?
Yes.
Right? Don't forget your minus signs though. Now, you can memorize all 6, it's fine, right? But when I was in school and learning calculus for the first time, I memorized this much. That was it. Because these formulas in here, I immediately seen as the modification on the 2 ones on the left. So it was very easy for me to memorize these formulas. Okay. The use of this should be clear. You are going to have a problem which is going to ask you to compute the derivative of x cubed times sine x. What method do we use?
The product rule.
Beautiful. We see the product rule because it's times, and we just unleash the product rule formula, and the problem is solved. So we're going to say copy the first, derivative of the second, derivative of sine is cosine, plus copy the second, which is sine x, times derivative of the first, 3x squared. So your uv became uv squared plus vu squared. This formula you learn in 3.4. If you haven't learned it yet, because maybe you focused on the exam and then you took the exam last weekend and you haven't done anything in a week because you're resting after the exam, then you didn't get to learn the 3.4 product rule, right? But we covered that last time, and 3.4 formula for product rule is right there. Actually, leave it. Why not? 3.4, whatever. Right there. So now we simplify this, which is going to be x cubed cosine x plus 3x squared sine x. And then you kick out x squared, and you get your x cosine x plus 3 sine x. And before you ask me, do we have to factor x squared? I will just say you don't. However, if you practice it now, you won't have to do it. You won't have to do and get used to it when you learn chapter 4. Because in chapter 4, we're going to take this problem and say equal to 0, solve it, and go further with this. So it builds up. And it's, if you set it equal to 0 here, you can't solve it. You have to have this in order to solve it. Like, you have to factor it as far as possible, because now x equals 0 and all of this mess equal to 0. It's easier and possible to solve. So factoring your answer that's really good to start, getting on that train now, because chapter 4 is coming up. I mean, that's something that is there. Here is another one that it's a big deal, and that is the derivative of e to the negative x times, let's say, cosine x. Now, if you don't remember the derivative of e from the first lecture, I'm just going to put both formulas. The derivative of e to the x is itself. If you change this x in any way by number in front, in this case -1, then the derivative is e to the ax is a e to the ax. So if you have e to the 3x, e to the 10x, and also e to the -1x, which is just negative x. It's again product rule. So can you please work this out for this real quick?
Professor, do you want an answer?
Did you factor it?
Yes.
Beautiful. What do you
I've
got?
e to the negative x. I factor it out.
Okay.
And within the parentheses, it is cosine x minus sine of x. I just rearranged it.
Okay. That sounds really good. We're going to have, again, product rule, so u and the v. And
Yes.
I learned it as copy the first derivative of the second. I kind of verbalized that rather than u v prime. You know, whatever, guys, makes you happy. So copy the first. Derivative of the second is going to be negative sine. Plus copy the second, which is cosine x. And then derivative of the first, which is negative e to the negative x. Right? Negative e, because that negative, yes, okay. Oh, so there is a negative there. Okay.
Oh, that I'm wrong.
I think you just, yeah, I think you just have the negative there. That's okay. It's not a big deal. I mean, come on, you did a lot. So now negative and negative, that's gonna factor, and e to the negative x is gonna factor, and then sine plus cosine stays inside. Now, so that was a pretty good, you know, that minus sign. So on 10 points, it's -2. Okay. So now it's still good. So now, why would something like this be important, right? Why do we study these things? Is this just to annoy students? So you have another calculus problem that you can, you know, get wrong? And the answer is no. If you study physics, right, and you understand that there is a pendulum hanging on the wall, on the ceiling, and then you pull it back to this position here and let go, it's gonna go past this way and go. And then you have the distance traveled d. If you graph this in time, you start with the distance of how far you pulled, and this is the time. And what happens? It drops down, it goes up, it goes, and then it stops slowing down, and eventually it stops. You know that there is air resistance and there is gravity. So anytime you let the pendulum swing, given enough time, it will stop. You will study this in differential equations in detail, but this is the mathematical formula which describes this motion, except you change these x's to t's, and then you see that the distance would be given by this formula. And what was the derivative of the position function? What do we get when we take the derivative of the position? Anyone?
Velocity.
Velocity. Change in position is meters per second or miles per hour. It's a velocity, it's a speed. So what did you compute here? That's a formula for speed. So when you plug in t equals 3 seconds, you know how fast this pendulum is moving at 3 seconds. Now that's important in design. I mean, you're not designing pendulums, but you understand where and how it kicks in. So this is not something that you are learning a math problem to solve the math problem. You always the question, where is this actually used? And that's where the true knowledge comes from. No one cares, no one will ever care that you can do the product rule and a quotient rule, especially now that you can plug that in a computer and get the answer, right? No one will ever care. The only thing that is important is that this part here is the mathematical model for the position function for the pendulum, and this formula here is the formula for velocity. And I can compute by plugging in t equals whatever seconds. I can calculate the position of where the object is. I can calculate the speed of the object, and I can take another derivative of this and get what? What do I get? I get acceleration, right? So we can also calculate acceleration. All of those things by working out some simple derivatives. So, and that's it. I hope you're not disappointed with the trig. I know it's short, but you guys have these 6 formulas. You can exploit the symmetry and the patterns in any way you possibly can to memorize this, or just flat out memorize all 6. You are going to use this, as I said, later in Calc 2. So if you are, planning on not learning this now, then you will have to learn it when you get to Calc 2. So I don't have to, here. Let's jump into Calc 2 and go into trig integrals and, start with all of these things. They're going to be there as a part of this substitution that is happening. See, u equals cosine x, du is negative sine x. The derivative happened between them. And clearly, later on, you're going to have all of your derivatives pop up. So this is the integral side, but then derivatives u and du. Do we all see the derivative written in blue? So this is me reviewing because some students simply did not learn it, and they can't perform at all. So its complete section is 0. So you need to learn these things and practice them. You have seen examples. The examples are mainly product rule and the chain rule. I can also ask for a tangent line, right? There will be a good example as well. So try that for homework, and we can start with that next time. So find tangent line at x equals pi over 6 for f of x equal cosine x. Well, you have to take the derivative to find, and then plug in pi over 6 to find the slope, and right, and then you can find the equation. So all of these things still, right? Tangent line is a question that you can ask in every section of chapter 3, because you're learning the way to take the derivative, and taking the derivative is what gives you the slope of the tangent line. So tangent line is a fair question for every single section of chapter 3. So you can try this for homework, and we can start next class, right? Next week. We can start with looking into this one, right? If you have questions now, if you just do it and you all know it, no need to ask question, then we don't have to go and do this. We're going to take about a 10-minute break now. We have been working very hard for hours. Previous stuff was obviously not streamed. We were dealing with the exam. We'll take about 10-minute break, and when we come back, it is going to be the most important lecture of chapter 3 and probably the most important lecture of Calc 1. So we'll deal with 3.6, the chain rule. if you want to prep for that class now, if you don't need a break, go look up function composition. I'm going to start with that. See you in about